everyone. In this video, let us study orthogonal vectors and subspaces. We know that xy plane is always perpendicular to each other. This can be extended to three-dimensional space or in broad sense on n-dimensional spaces. We can say that the axes are usually perpendicular to each other. This can be further extended to four fundamental subspaces what we have studied in the earlier videos. Those are column subspace, row subspace, left null space, null space, and we can say that they are also at right angles to each other. The two column and the null spaces are orthogonal to each other in the m-dimensional subspace, and the two row and the left null spaces are orthogonal to each other in the n-dimensional space. Once we know a vector in a space, we can compute the length of the vector. The length of the vector is always given by positive square root of x transpose x. We know the length is usually defined like this. So we know that x square is given by the components of the vector space x1 square plus x2 square up to xn square, that is given by x transpose x. Let us try to understand this by taking an example. Let us define a vector set given the elements 1, 2, minus 3. Then the length of this vector x is square root of x1 square plus x2 square plus x3 square. That is 1 square plus 2 square plus 3 square. And that gives you the square root of 14. In other words, I can write this as x transpose multiplied by x, that is 1 square plus 2 square, that gives you 5, plus 3 square, that is 5 plus 9, that gives you 14. So square root of 14. Let us try to understand the concept of orthogonal vectors. Given the two vectors, set x and y, x having the components x1, x2 up to xn, y having the components y1 up to yn. Then the inner product, the x transpose y, is given by x1 y1 plus x2 y2 plus so on up to xn yn. And this is usually called as scalar product or the dot product. You define it in the bracket x comma y or x dot y. The inner product x dot y, if it turns out to be 0, then we say that x and y vectors are orthogonal to each other. If x transpose y is greater than 0, then their angle is less than 90. If x transpose y is less than 0, then their angle is said to be greater than 90. We try to understand the concept of orthogonal vectors with two examples. The first example is we need to check whether the given vectors 2, 2, minus 1 and minus 1, 2, 2 are they orthogonal to each other. So we know that it is x dot y or x transpose y should give us 0 if they are orthogonal to each other. So I have written here x transpose 2, 2 minus 1 multiplied by y minus 1, 2, 2. So that gives you minus 1 into 2 minus 2 plus 2 into 2 plus 4 and plus minus 1 into 2 minus 2. So the sum of this turns out to be 0. So I can say that these two vectors are orthogonal to each other. Let us take the second example where we have defined the two vectors v1 and v2 as v1 is equal to cos theta sin theta, v2 is minus sin theta cos theta. We need to check whether v1 is orthogonal to v2. So we have X transpose into Y. That means in this case it is V1 transpose into V2 transpose. So cos theta sin theta multiplied by minus sin theta cos theta. That gives us cos theta into minus sin theta will give me minus cos theta sin theta. It has to be added to sin theta into cos theta. So when you add these two, it will be equal to 0, which means that these two vectors v1 and v2 are orthogonal to each other. Let us try to understand the concept of orthogonal subspaces. Two subspaces are said to be orthogonal to each other if every vector in one subspace is orthogonal to every vector in the other subspace. In general, I can say that two subspaces V and W can be said to be orthogonal provided every vector V in V is orthogonal to every vector W in W. That is, V transpose W is equal to 0 for all V and W. Even the subspace 0 is orthogonal to all the subspaces. Try to understand orthogonal subspaces by solving one problem. Let us take V is a plane spanned by the two vectors v1 is equal to 1, 0, 0, 0, 4-dimensional space. v2 is equal to 1, 1, 0, 0. If W is given by 0, 0, 4, 5, we need to find out whether W is orthogonal to the whole plane V. We know the expression V transpose W, that is given by 1, 0, 0 and 1, 1, 0, 0. It should be multiplied by 0, 0, 4, 5. So when we multiply this, it's a matrix multiplication. So we get the answer as 0, 0. And we can see that turns out to be 0, 0 vector. So therefore we can say that the W is orthogonal to the entire plane V. Let us see how a vector can be projected onto a line. B is a vector. We want to project this vector onto the line A. The shortest distance will be the distance formed by a line which is orthogonal to A. So I am projecting this B onto this A perpendicularly so that E and A are perpendicular to each other. The approximate value of E is equal to length of the vector B minus the length of the vector C. So E can be written as B minus C, the approximate length. So we know that this point C lies on this line A. I can multiply this vector A by a scalar quantity x. I can get the value of P. So P is equal to x into A. And we know that A is perpendicular to E. I can say that E and A are orthogonal to each other, perpendicular to each other, where E is given by B minus XA. And we know that A transpose B minus XA. Earlier we have called this as Y. That should be equal to 0 if they are orthogonal to each other. So when I simplify this, I get x into A transpose or x A transpose A will give me equal to A transpose B. I have simplified this and I get this x into A transpose A will be always equal to A transpose B. Let me get the value of x, that is given by A transpose B divided by A transpose A, and we know that P is equal to A into x. So it is A into x. X is given by A transpose B divided by A transpose A. Projection matrix. We try to project the point P on the vector A in terms of projection matrix P. And we know that the point P is equal to projection matrix P into B. And here we know that P is equal to x into A, where A is a vector in the, where this point P lies, and that can be written as A transpose B divided by A transpose A. So that means if you compare these two, we can write that the projection matrix P is given by A transpose divided by A transpose A. Let us try to understand the meaning of projection by this example. Let S be the plane spanned by the two vectors defined as V1 and V2. We need to find the orthogonal projection of the vector x equal to 4, 0, minus 1 onto the plane S. Also, we need to find the distance from S to S. Let us define x equal to P plus O, where P belongs to S and O is perpendicular to S. Then the orthogonal projection of S onto S is given as P, and the distance from S to S is given by the length of O. Let us define P is equal to alpha into V1 plus beta into V2, where alpha, beta are scalar quantities. They belong to the field R. Then we can write that O is equal to x minus P, where P is given by alpha V1 plus beta V2. Substituting this, we get O is equal to x minus alpha V1 minus beta V2. It has been told that both these the value O is perpendicular to the plane V. That means every vector in V has to be orthogonal to O. So therefore, O dot V1 should be equal to 0. O dot V2 also will be equal to 0. So we can write O is equal to x minus alpha V1 minus beta V2 dot V1 is equal to 0. Simplifying this, rearranging this into right hand side and left hand side, we get this as alpha into V1 dot V1 plus beta into V1 dot V2 will be equal to x dot V1. Similarly, O dot V2 will give us alpha V1 dot V2 plus beta V2 dot V2, that is equal to x dot V2. Now, alpha into V1 is defined as 110 multiplied by 110, that is V transpose V1 transpose V1 plus beta into V1 transpose, that is 110 multiplied by V2, that is 011. When we simplify this, we get this as 1 into 1, 1 plus 1 into 1, 1. So we get this as 2 into alpha plus here 0 into 1 is 0, 1 into 1 is 1. So I get multiplied by beta, we get 2 alpha plus beta is equal to x into x dot v1. So x transpose is given by 4 0 minus 1. It has to be multiplied by v1 1 1 0. So we get this as 1 into 4 4. So 1 into 0 is 0. 0 into minus 1 is 0. So we get this as 4. Similarly, we have alpha into v1 transpose multiplied by v2, that is plus beta into we have v2 transpose multiplied by v2, that will give us alpha plus 2 beta is equal to x transpose v2. So x transpose v2 is given by minus 1. See, we have two equations here. First equation is 2 alpha plus beta equal to 4. Second equation is alpha plus 2 beta is equal to minus 1. We need to solve for alpha and beta. Solving these two equations, we get alpha equal to 3, beta is equal to minus 2. So I can write the p value as alpha v1 plus beta v2, that is 3v1 minus 2v2. So that will give you 3 times v1 minus 2 times v2 will give me 3. 3 minus 2 minus 2. When I simplify this, I get this as 3, 1 minus 2. I substitute the value of v1. v1 is given by 1, 1, 0. So 1 into 3 I get 3. And 1 into 3 I get here 3. And 0 into 3 is 0. And minus, I have to subtract 2 v2. And v2 is defined as 0, 1, 1. So I have 0 into 2, it is 0 here. And 1 into 2, I get minus 2. And then I have 1 into minus 2. So I get this as minus 2. When I simplify this, I get 3, 1 minus 2. I can get O is equal to the point O can be found out, the vector O can be found out as x minus t, that is 4, 0 minus 1 minus of 3, 1 minus 2. That will give me, it is 4 minus 3 is 1 and 0 minus 1 will give me minus 1. Minus 1 plus 2 will give me 1. Now I need to find the length of this vector, that will give me the distance. So when I find the length, I am going to get square root of 1 square plus minus 1 whole square plus 1 square, that is root 3.
Let us try to understand the projection, orthogonal projection, with the help of two problems. W is the subspace spanned by U's. So W is spanned by U1 and U2, where U1 is given by 1, 3, minus 2 and U2 is given by 5, 1, 4. We need to write y is a vector defined as 1, 3, 5 as the sum of the vector in W, and also we need to find a vector which is orthogonal to W. When we project y onto this W, we have the equation y cap is given by u1 dot y divided by u1 dot u1 multiplied by u1 plus it is u2 dot y divided by u2 dot u2 multiplied by u2. That gives you, it is u1 is given as 1, 3, minus 2 it is dot 1 3 5 divided by 1 3 minus 2, this is u1, dot 1 3 minus 2, it is multiplied by u1 1 3 minus 2 plus u2, that is given by 5 1 4 multiply dot product 1 3 5 divided by 1 3 5 dot 1 3 5 5 1 4 5 1 4 5 1 4 multiplied by, it is 5 1 4. When simplifying this, I get 1 into 1 1, 3 into 3 9, minus 2 into 5 I get minus 10. Here 1 into 1 1, 3 into 3 9 plus minus 2 into minus 2, that gives me 4 multiplied by 1 3 minus 2 plus 5 plus 3, 4 into 5 20 divided by 5 into 5 25 plus 1 4 into 4 16, it has to be multiplied by 5 1 4. Minus 2. So I get this numerator term is 10 minus 10 0 multiplied by 1 3 minus 2, and here I get it is 28 divided by, it is 42 multiplied by 5 1 4. So I get this as 28 by 42 is given by 4 by 6 5 1 4. Further reduction, it is 2 by 3 5 1 4. So I can write this as 10 by 3, 2 by 3, 8 by 3. This is equal to y cap, and if you want to find the vector which is orthogonal to W, then we should find y minus y cap, that is y is given by 1 3 5 and y cap is given by 10 by 3, 2 by 3, 8 by 3. By simplifying this, I am going to get the answer as minus 7 by 3, 7 by 3, 7 by 3. If somebody asks you to find the length, then it is y minus y cap is given by square root of 7 by 3 whole square plus 7 by 3 whole square plus 7 by 3 whole square. So I get this as 3 times 7 into 7 is 49 divided by 9. So I get this as square root of 49 by 3. This is the answer. In this problem, we need to find the closest point to y in the subspace W, which is spanned by W is equal to V1, V2, where V1 is given by 3, 1, minus 1, 1. V2 is equal to 1, minus 1, 1, minus 1. And the vector y is defined as 3, 1, 5, 1. Like the previous problem, we'll try to find out y cap. It is given as v1 dot y divided by v1 dot v1 multiplied by v1 plus v2 dot y divided by v2 dot v2 multiplied by v2. Substituting the values, I have v1 is 3, 1, minus 1, 1 and y is 3, 1, 5, 1 divided by 3, 1, minus 1, 1 dot 3, 1, minus 1, 1 multiplied by v1 3, 1, minus 1, 1 plus it is v2 1 minus 1, 1 minus 1 dot 3, 1, 5, 1 multiplied by it is 1 minus 1, 1 minus 1, it is dot 1 minus 1, 1 minus 1 and it is multiplied with value v2 and v2 is given by 1 minus 1, 1 minus 1. When we simplify this, we get 3 into 3, 9, 1 minus 5 plus 1 divided by 9 plus 1 plus 1 plus 1. 3, 1 minus 1, 1 plus here I get 3 minus 1 plus 5 minus 1 divided by 1 plus 1 plus 1 plus 1 and multiplied by 1 minus 1, 1 minus 1. So you get this as, when you simplify this, final answer will be 3 minus 1, 1 minus 1. So we have y minus y cap, that is the vector orthogonal. So we get this as 3, 1, 5, 1 and 3 minus 1, 1 minus 1. That will give us 0, 2, 4, 2. We are supposed to find the closest point to y in the subspace. So we need to find the length of y minus y cap. So y minus y cap will give me the square root of 2 square plus 4 square plus 2 square. That gives me square root of 24.
Thank you. In the next video, let us solve some problems under orthogonal projections as well as orthonormal.